Okay, great. So I think we can go ahead and get started. So welcome everybody to this talk, and I'm really pleased today to be able to welcome Dr. Clark Miller. He is the director of the Center for Energy and Society and a professor in the School for the Future of Innovation in Society at Arizona State University. He is also the co-editor of The Weight of Light, a collection of solar futures, a free downloadable book of science fiction stories and other writings about the future of societies built using solar energy. And so I think without further ado, welcome, Clark.
Thanks, Suzanne. It's great to be here. So would you like me to just launch in?
Dive right in. Yeah.
All right. Let me share my screen here. All right.
Beautiful. Okay.
So let me, while we're doing this, just click a few buttons and then do that. And you all should see my screen. Do you?
I do.
Great. All right. So thanks. I really appreciate the opportunity, and I really wish that I could have been there in person with you all to explore these ideas in a variety of ways. But I think we're all extremely lucky that Zoom figured out how to do what Zoom does really well about a year ago, and we learned about Zoom along the way, and discovered that it made things really easy. It turns out making things really easy comes with some problems, which we're now figuring out as well. But at least we have the opportunity to be here and to talk about this stuff anyways. As Suzanne mentioned, I run something called the Center for Energy and Society here at ASU, which is our effort, and it's one of the relatively few institutionalized efforts around the country to understand what energy transitions will mean for people, not just for technology. And I'm sure those of you who've been taking a class with Suzanne have been introduced to this idea before, that we have to think about what all of this stuff means in human terms. And so hopefully none of this will be entirely new to you. It's also something that I do in relationship to a center called the Quantum Energy and Sustainable Solar Technologies Center. This is an NSF-funded center focused on solar energy and particularly on photovoltaic technologies. Here at ASU, it's a partnership with about 8 other universities around the country. It is almost 100% engineering focused in terms of the guts of solar panels, but it's why you will see over the next 20 slides or so that I'm really focused on solar energy, is because I've been spending a lot of time with the folks who make PV panels smarter, more capable, and especially more efficient and more inexpensive. And so we've been thinking a lot about the future of solar energy. I think everything that I say applies to other forms of low carbon energy technologies as we go forward. But there's a particular reason why we also focus on solar, which we'll get to in a little more detail in a few slides. And that is that almost everybody thinks that if we're going to get to a low carbon economy by mid-century, which is kind of everybody's target at the moment, we are going to rely heavily on solar energy to get there, especially globally. There's some discussion in the United States about about whether solar or wind will be more prominent in the portfolio by mid-century. But most places around the world, it's pretty clear, will be solar heavy more than they'll be wind heavy. And that as a result, something like half the world's energy supply in 2050, if we get to a carbon neutral economy, will come from photovoltaics. And so it is a significant piece of the puzzle, regardless of what other technologies we build alongside of it in order to meet global energy needs in 2050. And so that's besides just the opportunity of working with a bunch of photovoltaics engineers over the last 10 years, there's also a reason why we've been focused a lot on solar energy. So let me start by just observing that in many, many, many ways, we live in a world that's designed by, for, and around carbon. We don't always think about all of the different ways that our lives and our economies are organized around carbon, but they really are. And I find one of the most helpful illustrations of this is from a 1950s children's book called What Do People Do All Day? Written by an author called Richard, whose name is Richard Scarry. He has another book that's almost as famous. Both of them are set in his fictional community of Busytown, which is called Cars and Trucks and Things That Go. And that one's really all about, as you can imagine, the internal combustion engine, the automobile, and the world that we have created for automobiles. This image that I'm showing you here is rather about the electricity system. And of course, these are the two big energy systems in the world, right? The fuel energy system that we use for our cars and our trucks and our airplanes, and to some extent for a few other things like heating buildings in the wintertime, particularly in the northern tier of the United States, for a little bit for cooking, natural gas, for water heating, and other kinds of uses, but predominantly for moving around in the world is one of the big energy systems. And the other one is, of course, electricity. And this is a picture of the electricity system. And at the heart of it is a big coal-fired power plant. And coal has been at the heart of the electricity system since its beginning here in the United States and elsewhere as well. And of course, you can see the supply chain coming in from the left-hand side of the picture, the coal train that brings coal to the power plant. The previous page is the coal mine, right, where we're digging the coal out of the ground and putting it on this train. Of course, you can also see the distribution system, right? The transmission grid and the distribution grid through which we deliver electricity to our houses and our businesses and our workplaces. And of course, all the machinery that's involved in that. But everywhere else in this picture, we also see, and this is the point, a bunch of people. And those people's lives are directly organized around this steam-fired power plant, right? So we have coal miners on the previous page. We have a train driver that is driving this coal train. Most of you will also know that today the railroad industry is profitable largely because we've been moving oil around on trains in the United States in a really, really, really big way. So trains are still an important part of our energy infrastructure and our energy supply chains. We have the bear in the boiler room who's saying it's hot in here, reminding us of workplace dynamics that we have to pay attention to that have been critical to the history of industrialization and the role of workers in factories and in places with lots of machinery. I love the little pig who sits on top of this coal-fired power plant. He's reading a book, a textbook titled Ohm's Law, which as a young electrical engineer, I learned in my very first electrical engineering class. That pig reminds us that when we invented the electricity system in the late 19th century, we also invented a whole new discipline to go with it called electrical engineering. Electrical engineering today is the largest major and the largest department on many campuses. I don't know whether it is at Oklahoma or not. It certainly is here at ASU. And it was where I graduated as a young electrical engineer at the University of Illinois. Most people aren't aware that we built the first electric power plant in the United States. Thomas Edison built it and started selling electricity in 1882. And that very same year of 1882, MIT offered the first electrical engineering curriculum in the United States. So you see the tie between our educational system and this carbon-based electricity infrastructure that we built in the late 19th century. But there are sort of many different facets of our lives that are organized around this electricity system in a way, and also the automobile system, in a way that we don't often stop to think about, right? But if you look in the upper left-hand picture, right, where you have these giant highways and you have these this picture of a suburb, this landscape was really organized around the automobile. And if you live in a place, I don't know how it's like in Norman and Oklahoma City, but because I haven't never been there and I was looking forward to it. But if you live in Phoenix, you'll live in a city that was built for automobiles. It is nearly impossible to be a pedestrian in this city. It's nearly impossible to be a bicyclist in this city because everything was designed for cars. Our urban landscape has been organized around the automobile. If you look in the upper right-hand corner, you see a picture of an amusement park. It's a little known fact about amusement parks, but they were invented by the electricity industry for a very simple reason. Let me go back a page. This coal-fired power plant, one of the features of this coal-fired power plant is it really, really, really hates to be turned off. It really doesn't like it. So much so that in the early electricity industry and today, they simply don't turn coal-fired power plants off. They produce the same amount of electricity day, night, summer, winter. It just doesn't matter. It just produces the same amount of electricity every minute, every day. But the consequence of that in the late 19th century, late 1800s and the early 1900s was we did not live in a society that operated that way. We live today in a 24/7, 365 culture. And that culture is at least in part a result of this coal-fired power plant right here on this screen. Because that early electricity industry had electricity at night that nobody wanted because we were living in a society that was diurnal. We got up and in the morning and we ate breakfast and then we went to work and we did our work and we consumed energy in the middle of the day. And in the evening we went home and then we went to bed when the sun went down and we quit using energy. And that society was deeply inconsistent with the way that this coal-fired power plant liked to run. And so the early electricity industry spent an enormous amount of time and energy trying to figure out how to get the rest of us to use electricity at night. And part of the way they did that was just basic economics. They made it really cheap. They had an excess supply. There was very low demand. Economics 101 tells us what happens when you get that situation, right? The price drops and it drops dramatically. In fact, the early electricity industry gave away electricity at night in many instances at lower than the cost of production because it had it and nobody wanted it. But the other thing that they did was they went looking for ways that they could increase electricity consumption at night that didn't just involve lowering prices. Turned out that wasn't enough. And so they started investing in industries. And one of the things that they invested in was street lighting. And so that's this middle picture in the top, right? The electricity industry spent a lot of time convincing cities that they needed to light their streets. And I think it's not an accident that this was the time, for example, when stories about, for example, Jack the Ripper circulated widely in Victorian society, right? Because among other things, the electricity industry was trying to make the case that they could help make cities safer by lighting them up at night. Turns out they also wanted those lights to drive changes in business. And so they invented the idea collaboratively with big downtown shopping areas of creating what would be the precursor of a much later invention, the mall, right? The idea that in the evening you would, instead of going home and eating dinner and going to sleep, you would instead go downtown in Chicago, for example, to the Magnificent Mile, or in New York to Broadway, and you would be entertained and you would be able to shop in a fully lit up, exciting place to be, was part and parcel of the electricity industry trying to figure out how to get people to use electricity at night after work. And amusement parks were the same way. Amusement parks use electricity at night and on the weekends. And most of the time in the early 20th century, they were located at the ends of an electric tram line. So you got the electricity for moving the people out to the amusement park, and then for running the rides at the amusement park and the lights and everything else. And then when people were done, you got the electricity of moving them back into the city, right? And so you can see this idea of how are we going to get people to consume energy. It also turns out that most people don't know this, but the electricity industry invented television. So the first television station in the United States was made by General Electric. General Electric was Thomas Edison's company that went alongside the electric utilities. So the utilities are the people who sell us electricity. General Electric was the company that sold the utilities the equipment that they needed in order to run the electricity system, right? So it was like an inner circle, if you will, right? So Edison sold electricity to you, and then he sold equipment to the utility, right? Well, General Electric, though, very quickly realized that they could also sell stuff to you and me so that we could use more electricity, right? And so they sold toasters and they sold refrigerators and they sold stoves, right? So many of you may have in your kitchen a GE refrigerator or a GE light bulb or a GE stove, right? All of that stuff was sold to you by General Electric for the purposes of enabling you to consume more electricity, and particularly to consume it at times other than the middle of the day, right? So at breakfast time when you first got up in the morning and in the evening when you got home. And they also invented television, right? So the first television station was on General Electric's Schenectady campus. The first radio station was on General Electric's Schenectady campus. And they were investing in radio and television because they could sell all kinds of things with radio and television. They could sell the electricity to run the broadcasting station. They could sell the electricity to run your television to receive the signal. They could sell the television that allowed you to watch TV, and they could sell the camera that allowed the company, the TV station, to film the TV signal. General Electric sold all along that chain, and it enabled them to make more use of electricity at night. Some of these other pictures, the one in the bottom center is of San Francisco, and it's the old coal-fired power plant that was the central station for San Francisco's electricity system. You can find those kinds of central stations in many, many cities in the United States. Most of them no longer operate, but they operated for decades as the heart of the early electricity station. The bottom left picture is skyscrapers. I learned this just the other day. It's really interesting. Skyscrapers can't exist without electricity because they require elevators, and you can't run an elevator without electrical energy to move people 40 floors into the sky. And so skyscrapers as buildings emerged at exactly the same time that electricity systems emerged to enable you to move people vertically through the building. And of course, they also have nowadays, especially highly centralized heating and air conditioning systems, many of which also run at least part of their energy supply is electricity. So we have really shaped many facets of our communities, our materials, our geographies, and our cultures around the use of carbon and the way we transform carbon from a material substance into a form of energy that we can use as human beings, both on the fuel side and on the electricity side of our energy systems and of our societies. I have one more thing to say about that later. But what I want to highlight, right, as we think about this low carbon economy future that we're talking about, right, is that the power system that we have used to generate energy is rapidly changing, right? And I think we all think about energy transitions. We all recognize the complexity of those transitions. And for folks who think about climate change and the debate about climate change, I think many people would like to see us transition faster. But I want to emphasize that this system is already changing very rapidly. And so just as an illustration of that, here you see up through 2018, new additions in the electricity sector alone of renewable energy technologies. And in particular, I want you to look at the yellow line in 2018. We added 181 gigawatts of new photovoltaic, almost all of it photovoltaic energy power plants in 2018. Just to give you a sense of the scale of that, the state of Arizona, our peak capacity when we're running full out in the middle of the summer, cooling the state in 120-degree temperatures, we're using about 30 gigawatts of power to power the state of Arizona. So we're talking about just in 2018 alone, we added enough solar energy to power 6 states the size of Arizona, right? 6 cities the size of Phoenix. We've got 5 million people, right? So you're talking about 30 million people worth of new solar energy added to the grid in 2018 alone. Now, this is worldwide, so keep that in mind. I'm going to show you another picture now, which is the same, a similar data set, right? But now showing in blue the new renewable energy additions that we've made. And and in gray, the non-renewable energy additions to the grid. And what you can see here is that from 2015 on, we have been in a context where we are adding more renewable energy to the grid then we are adding non-renewable energy to the grid. And almost all of that gray that's being added now is new natural gas power plants. We have stopped building coal-fired power plants in the United States at this point. And in fact, we're rapidly retiring them. So in Arizona, last year at the end of 2019, we retired the largest coal-fired power plant in the state. I just saw a presentation earlier this week by the Salt River Project, which is our largest utility here in Phoenix. And their plans for the next 12 years include closing every single one of their coal-fired power plants, right? And so we're really moving rapidly into a world in which renewable energy and natural gas provide the vast bulk of our electric supply. And here's a projection from McKinsey. So McKinsey is a global consulting firm. Their clients are organizations like Bank of America, JP Morgan, ExxonMobil, right? The biggest companies in the world go to McKinsey, and they get McKinsey to tell them things like, what's the future going to look like? So this is their December of 2019 projection of what the future of energy is going to look like. From 2015 to 2050. This is the same thing that we were looking at in the last two slides for the past, only now looking at for the future. What new kinds of energy power plants are we going to build between now and 2050? And what McKinsey thinks, and they're not out of line with any other projection that I've seen, of what that's going to look like, is that 82% of our future energy build is going to be solar and wind. And of that 82%, 64% is going to be solar. So between now and 2050, we're going to add, and if you just add up, what does that mean in terms of an actual number? We're going to add 7.7 terawatts of new photovoltaics to the world's energy systems in the next 30 years. So that's 7,700 gigawatts. Remember, I said Arizona uses about 30 in the middle of the summer, right? So if you just divide that, 770 divided by 3, you know, it's roughly 250 energy systems needed to power a state the size of Arizona. We're going to do that 250 times worldwide, just in terms of the new solar energy that we're going to build. Another piece of this change, though, that it's absolutely critical to kind of think through is that we're also going to shift the energy end use. So right now, worldwide, we use about 20% of our energy in the form of electricity. So usually what you see is a kind of three-part picture. We use 1/3 of our energy to produce electricity. We use 1/3 of our energy to run our cars and our trucks, and that's almost all, and our airplanes. Airplanes are a little piece of that, just a little piece. That's mostly gasoline, some diesel, a little bit of jet fuel. It's all fuel though, almost all fuel, right? And then 1/3 of our energy is in buildings. And that means we're heating buildings in the winter. We're cooking. We're running industrial processes inside buildings. So we're creating industrial heat for things like making steel or other kinds of industrial processes. Right? So usually you see this as 1/3, 1/3, 1/3. But what that picture ignores is that 1/3 of the energy that we produce when we consume fuel, when we burn a fuel like gasoline or kerosene to create energy, 1/3 of the energy is lost immediately in the form of heat. And so that 1/3, 1/3, 1/3 that you usually see doesn't count that 1/3 of the fuel energy that we've already lost as heat, because we don't use it productively for the most part. In fact, even in our industrial processes where we're looking for heat, we waste most of the heat that we generate when we burn fuels. And so what we're looking at going forward is many of those processes that use fuel at the moment, and electric cars are a really good example of that. As we move toward a low carbon economy, we're going to change from burning fuel to consuming electricity. And so we're likely to see our electricity system rising from something like 20% of the world's energy consumption, final energy consumption, the stuff we actually use to do work or to move around, right, to 65%, maybe 75%, maybe even higher. Now, there are some things that don't electrify well, and so we may need to continue to use fuels in those circumstances, and that means we have to do other kinds of things. We either have to create clean fuels, so hydrogen, for example. There's a lot of effort going into thinking about how do we build hydrogen fuel systems for those few things that we need heat, or we might capture carbon and recycle it. So capture it out of the waste streams of our fuel burning processes and turn it back into another fuel so that we can use it again. So usually what people imagine there is that we will use photovoltaics to take the carbon and water and mix them back together to create a new renewable fuel. So that too will increase the amount of electricity consumption that we need. So as we go forward, we're really talking about two big changes to how we produce and consume energy. And that is we're shifting to electricity from fuel, and we're shifting more and more towards renewables, and especially towards solar energy as the source of most of our energy system. And the question that we've been asking ourselves, to go back to that original point that I made, that our societies are optimized around carbon at the moment, is what will it mean for our societies to shift out the energy system? But we're also influenced by a lot of work that's been done thinking about technology and society over the last 40 or 50 years, that really emphasizes that it's important not to think about this problem in terms of, hey, we're going to build a new technology and then we're going to watch and see what happens to society afterwards, right? So that kind of technology driven process. Instead, we've been thinking about it from the standpoint of design, right? If we're creating new technologies to run our energy system, and that means we're going to need to rethink how we organize our cities and our cultures in order to make sense of that future, and in order to optimize our future around a different set of energy supplies. What are the design choices that we have in pairing up ways of organizing society with ways of organizing technology? Can we identify what some of those design options are? And can we use that to guide some of our thinking and to open up questions that as societies we might want to ask about the future of energy? Oh, sorry, I didn't move forward. So, trying to think about this, right? What are these human futures that might be powered by solar energy? And I hope at least some of you have had a chance to look at the book, The Weight of Light, that Suzanne mentioned earlier and that we circulated to you, because it has some of the efforts that we've been doing. That's one example of what we've been doing to try to think about what are these human futures that we might organize around solar energy. And how can we think about that? How can we bring that to a more everyday conversation so that it isn't just people who are technically trained to think about photovoltaics and transmission grids and other kinds of energy technologies. But really, it's all of us who can participate in these conversations and think about these kind of human futures powered by low carbon energy sources. And so we're really, trying to think about what is a photon society? What might a photon society look like? What are the kinds of infrastructures and supply chains that power those photon societies? What do they look like materially? This is one of my favorite pictures recently. This is a floating solar field in China. Really, really interesting questions start to arise about, okay, if you want to put 7.7 terawatts of photovoltaics down on the planet, where do you do that? How do you organize that? Do we put it all on our rooftops, our parking garages, our parking lots, maybe even above our streets? I mean, I got to tell you, here in Phoenix, that makes an enormous amount of sense, because it's only about through the end of this month that we want to actually see the sun. After the 1st of May, we would just as soon be shaded. And so building a whole bunch of solar shade structures makes a lot of sense in Arizona. But in other parts of the world, it might not be easy to put solar panels down in cities. It might not be easy. There might not be a lot of available land, although there's some really interesting new ideas emerging about how do you integrate solar panels into agricultural landscapes in order to optimize the benefits for both food production and energy production. So I think we're going to see a lot in that space going forward. Not everywhere has, deserts where you can go out and build a giant new solar plant out in the desert. And so water might be a place where you want to put solar panels. Now, I mean, you trade off a little bit potentially on the lifetime of the solar panels. Nothing kills solar panels faster than letting water inside of them. So you got to figure out how to make sure you don't get that water inside the solar panels. But anyways, it's really interesting questions about where are we going to put all these solar panels? But then what do these mean for the kinds of cultures and the kinds of communities that we will live in going forward? And so let me just run you through quickly, and this will be the last thing that I do, some of these design parameters, and think a little bit about what are some of the things that we need to grapple with going forward as we think about, how do we build societies powered by solar energy. So, this first one, same as the one I've just been talking about, size and distribution, right? Where do we put these panels? How big do we make the systems? I just put a set on my roof. It's about 8 kilowatts. Saudi Arabia has proposed building a 200 gigawatt solar power plant out in their desert. And you can see the picture on the left of the size of that power plant compared to the city of Chicago. I mean, you're talking about a power plant that's as big as the city of Chicago. There are lots of different ways to do this. One of the biggest obstacles that we've had here in Arizona to solar development occurred because of the bottom right picture you see there, the Macy's that put solar panels on its roof. It turns out we've got a lot of big box retailers, a lot of Walmarts, a lot of grocery stores, a lot of department stores here in Arizona, and they all have big flat roofs that are ideal for solar energy. And when they started getting excited about solar energy, it freaked our utilities out because they're big energy consumers and they have a lot of money that they can, they have, daily revenue streams that are big that they can just build a lot of solar energy. And so about 5 years ago, we had a little kerfuffle about that. It kind of put the clamps on the solar industry in Arizona for about 4 years. It caused a big political fight. Fortunately, we're now in a situation, I may need to move inside here, so bear with me as I walk. A a little bit of noise going on the street out there. But the, you know, and we're now in a situation though, where all of our major players in the state have wrapped their heads around this idea, and everybody has a target now of 100% carbon neutrality for their energy supply by 2050. So you can see that the, you know, these processes are moving forward and changing, but it still leaves open this question, you know, how are we going to build the future of solar energy in Arizona? Are we going to see more pictures like the top right, where you put a lot of solar on individual household rooftops? Are we going to see more solar on big box rooftops? Are we going to see, as the picture in the back suggests, large solar fields, large solar power plants out in the desert? Or, you know, one of my favorite ideas, which is at the heart of one of the 4 stories that you read, called Dividing the Light, which is the idea we might just build a giant solar shade structure for the entire city of Phoenix, right? And just to give you a sense of the scale, that power plant would produce enough electricity, right? If we just covered Phoenix with an enormous shade structure that was 50% coverage, right? So half the space was covered by solar panels and half the space was empty. Plants love that. They just love it in Arizona, because otherwise it's too hot and too intense, right? But if you did that, you could produce enough energy to power the entire western third of the United States, right? So everything from the Rocky Mountains west, we could produce all the electricity and all of the fuel, equivalent fuel needs of California, Washington, Oregon, Arizona, Utah, Nevada, Colorado, New Mexico, Montana, Wyoming, Idaho, right? All of those states, we could power all of their energy needs just from Phoenix, just from a big shade structure over a big city. So really interesting questions about where are we going to put all these solar panels? The second big question, and for me, this is in some sense the other big important question that really confronts us, is who's going to own all of those solar panels? So if you take a kind of the cutting edge solar panel, so we have a company here in Arizona that is the largest and only major US manufacturer of solar panels. It's called First Solar. They build the cheapest solar panel on the planet at the moment. It's a 440 watt panel. It's 2 square meters in size. And so if you take that panel at its current price, over its life, its guaranteed life, which is 25 years, that panel will produce about $1,500 worth of net revenue, right? So it costs, you know, $150 to buy it, costs another $150 to get it installed and set up. It produces $1,800-ish worth of electricity. You subtract, you get $1,500. It takes 39 billion of those to produce that 7.7 terawatts that McKinsey is estimating we will need, right? And so that that's 39 billion times 1,500 is about $60 trillion worth of energy. So the question of who owns those solar panels is fundamentally a question of who gets those $60 trillion worth of money, right? So just a reminder, a couple of weeks ago, Congress passed the largest rescue package for the American economy ever passed, right? And it was a $2 trillion piece of legislation. And the week before, the Federal Reserve Bank had made $4 trillion worth of money available to businesses and banks in the United States in order to help keep them alive in the middle of this crisis. So $6 trillion worth of stimulus package. The ownership of solar energy going forward is $60 trillion worth of money. It's a $60 trillion question, right? And so the question of who is going to going to reap the benefits of that as the owners of those panels makes an enormous difference, right? To all kinds of questions about the future of society, right? So let me go back a page and highlight this picture in the upper right-hand corner of this neighborhood in Phoenix with some solar panels on the roofs. Let me give you two scenarios, both of which are very real, for how that future looks in America. Okay, imagine an America in which we have solar panels on many of the rooftops. So now I'm going to get you to think about two different scenarios of that future. In one scenario, the people who own those houses own those solar panels and get the $1,500 per panel benefit of producing that electricity, whether they get it because it offsets their energy bill, their utility bill, or they get it because they sell some of that electricity back to the utility and put it out on the grid, right? Either way, they will generate, something like $1,500 worth of revenue for every solar panel on their roof. Okay, so that's one scenario. Second scenario, same rooftops, same solar panels, same locations. Nothing has changed in terms of the picture that you're looking at. In that scenario, however, all of those solar panels are owned by Elon Musk. Okay, so Elon Musk owns a company called SolarCity. And SolarCity is one of the largest companies in the United States that rents solar panels. They basically will put solar panels on your roof for free. And then they will give you a credit on your electricity bill for the energy that's produced from those panels. It amounts to, a modest kind of contribution. Right? But most of the benefit flows back to SolarCity, right? So now imagine every rooftop in America has a free set of solar panels on it that are all owned by SolarCity, and SolarCity is generating all of the revenue streams that come from all of those panels. Those are two radically different futures, right? One in which you have a very libertarian model of how you organize society, in which each of us owns our own assets and are part of markets where we buy and sell houses, we buy and sell solar panels, we buy and sell the electricity from those solar panels, right? So it's a very libertarian model of what the future might look like. At the other end of the spectrum, you have a model in which one company monopolistically owns all of the solar panels in America. Right? So they're totally different economic futures, and we haven't moved a single solar panel. Right? So ownership matters hugely. And all we've done so far is explore the question of private ownership of those panels and who gets to play in the private markets for owning solar panels. But there is equally a question of whether we might adapt other models of ownership to have some of those solar panels owned by non-private entities. So could be by cooperatives, could be by public ownership. So just as an example, here in Phoenix, we have two utilities. SRP, who I've talked about, runs the east side of the city. APS runs the west side of the city. They're about the same size, at least in their Phoenix operations. SRP is a publicly owned utility. APS is a privately owned utility. When we set up the electricity system in America 100 years ago, we had two models, public power and private power, and they thrive. Both of them thrived. So today, about 75% of electricity customers are served by private what are called investor-owned utilities. But 90% of the utilities in America who serve the other 25% of the customers, are publicly owned. There are over 3,000 publicly owned utilities in the United States at the moment, electric utilities. And then there's this other model, which is the bottom right-hand corner, which is this model of solar, of community solar, community energy, right? The idea that you and your neighbors might collectively put together a solar project for your neighborhood that benefits you as a community, right? And so there are many, many models of energy ownership that exist in the world at the moment and that might exist in a solar future or a renewable future more generally, and which will have a big implication for what kind of societies we live in at the end of the century. So ownership is, in addition to kind of size and distribution, ownership to me is the other big giant question of the next 30 years and energy infrastructure. But there are others. So I love this picture, this idea of aesthetics. There's an organization called the Land Art Generator Initiative, and they run global design competitions for creating giant renewable energy art projects in the middle of cities as kind of iconic statements of the significance of renewable energy. So this is an example from their competition that they ran with the city of Copenhagen in Denmark. And it's called the Solar Duck. And the idea was you would have a giant floating duck made out of solar panels in the middle of Copenhagen, of Copenhagen's, canals system. So aesthetics is something that I think we have not attended very much to in the history of energy to this date. Our energy infrastructure tends to be remarkably ugly. Think back to those pictures of power plants, giant smokestacks spewing forth smoke, giant refineries spread out across the landscape, giant highways moving cars in and around our cities, right? None of these is, to say the least, attractive as urban form. But one of the things about solar, and of course wind has some of those same issues, right? Turns out the more efficient you want your wind turbine to be, the bigger you have to build it. And so the most efficient wind turbines that we have are the ones that you can see from tens of even hundreds of miles away because they're so tall, right? So they dominate these landscapes. Solar turns out not to be like that. And in fact, it turns out to be highly artistic. You can make it highly artistic. You have to work at it a little bit, but you can make solar panels virtually any color you want. You can make them in virtually any shape that you want. You can make them into flowers. You can create very thin layered coverings for solar panels that don't impact the light, and in fact might even help the light properties of the panel, but which have paintings on them, right? So there's all kinds of cool things you can do with the aesthetics of solar panels that it's harder to do with some other kinds of energy infrastructures, and something worth thinking about. What kind of aesthetics do we want our future energy system to have? Life cycles are also absolutely critical. We did a little calculation. If you want 7.7 terawatts of solar energy, and it has a 25-year lifetime, and I'm hoping and praying that we get to the point where we build them with 50-year lifetimes rather than 25, just for this reason I'm about to talk about. But if it only has a 25-year lifetime, which is what we guarantee at the moment, you're going to have to put up and take down annually, globally, a solar infrastructure that's the size of 6 cities the size of Los Angeles, right? So the annual churn right? The annual destruction of used solar panels that no longer work and they're recycling, because we have to recycle all of that stuff. We cannot let this become another electrical industry with respect to the amount of electronic waste we produce in the world, right? So, how do we recycle 6 cities worth of Los Angeles full of solar panels in a given year? And then how do we rebuild that, right? It's a giant construction industry worldwide around solar energy, which is why the lifetime is going to matter enormously to the future of the industry. Because it's a 50-year lifetime, then it's half this, that construction, annual construction and destruction cycle is half the size, right? So it really matters. But other parts of life cycles, this is a lithium mine in South America. Lithium is, of course, the central component of batteries, lithium ion batteries, which we use in electric vehicles, which we increasingly use in grid storage for the electricity system to move solar energy from the middle of the day when it's bright sunshiny outside to when we want to use energy in the rest of the day, et cetera. So life cycles are important. Ecosystems are important, right? So in terms of thinking about building a city that is powered by, or building a world that is powered by moving electricity around from place to place, which is what we do at the moment, is very different than building a future in which we build electricity systems that are more localized, more distributed, more networked, right? Just different. So the picture on the middle in the right is of a vision of something called the Asian supergrid, which would be a giant transmission infrastructure that would move power all over Asia. It's the brainchild of the guy in the bottom right. He's the head of a Japanese company called SoftBank, which just in the last 2 days is not doing very well in the current scenario. They've had a lot of their investments go belly up, but so these ecosystems are important. Transportation, how much of transportation do we electrify versus turning into a hydrogen based fuel economy? It matters a lot in terms of the kinds of infrastructures that we have to build and the kinds of societies that we have to build. In the bottom left, you see a smart grid, a smart home energy management system. This is another piece of potentially our energy future in which all of our devices are connected to each other and talk to each other about all kinds of things like, whether we need to go to the store to get milk, or which of our devices can turn off at any given moment in order to adjust to some condition on the electricity grid where we need to reduce demand, right? So lots of interesting questions about ecosystems. And then I think the final kind of aesthetic question, or not aesthetic, but design question that we really need to grapple with is this question of abundance. Is the energy future one of ubiquitous, cheap energy? And there are lots of reasons to think that it might be, right? Every energy transition in history has unlocked an order of magnitude larger energy consumption by our societies on a per capita basis, right? So it's not just because we're growing our populations. We are using more energy per person right now than people were 100 years ago, than people were 100 years before that, by lots and lots and lots. And there's and one of the things about cheap electrons, which photovoltaics provides already and may provide even more in the future, is that there's a lot of solar energy to capture and a lot of potential electrons to create in that future. So it could be very abundant. But I have also been talking over the last 2 years with a lot of folks from Europe. And Europe is in a very different world right now, one that in which the principal conversation is one about living with energy scarcity. They believe that the primary answer to solving climate change is to make energy systems more efficient, to use less energy to do the stuff that we do in society. And there's a good reason for that. And that is that, in some sense, the cheapest energy on the planet is the energy you don't use, right? Is much cheaper in most cases to invest in technologies that will make your economy more efficient in terms of the energy it uses. It's much cheaper to do that than to buy and build new energy systems to produce and distribute that energy, right? And so there's a lot of argument about the value of efficiency and conservation to making this energy transition happen. So a lot of good arguments on both sides, but I can tell you it makes a huge difference in terms of the kinds of societies that we will inhabit in the future if those societies are using, let's say, 75% less energy per capita than we are today versus, let's say, 300%, 3 times as much energy per capita in the future. Those will be radically different futures in this question of scarcity versus abundance. All right, so let me skip through some of these here at the end just so that we can get to Q&A. But let me stop here because I think this one is interesting, right? This is a picture of the Earth at night. Of course, they've manipulated it so that they've been able to create a picture that doesn't have any clouds, and you never see the Earth without clouds. There are always clouds. But, this is what it would look like if you could see through the clouds on a given night in the world. And what we see here is energetic societies, right? We see societies that consume an enormous amount of electricity at night. And that is precisely because coal-fired power plants really hate to be turned off. If we had built the energy infrastructure of the early 20th century with natural gas power plants rather than coal-fired power plants, we wouldn't have this problem, because you can design natural gas power plants so that they ramp up and down as fast as demand. But we didn't. We built them with coal, and coal power plants don't like to be turned off. And as a result, we had a lot of excess energy at night. And so we figured out ways to use it and incentivize it and create it. And we built, as I said earlier, a 24/7, 365 globalized culture. And we build it all over the world. And as a result, we have these lights at night all over the world. Well, it's an interesting question of what happens going forward. So let me talk about two pieces of that world going forward. So first, I got to talk a little bit about this world that you see here in this picture. A lot of what's happening here is not just light, it's also activity. And in particular, there's a lot of industrial activity that happens at night because businesses have been incentivized to use cheap electricity, just like cities, which were using streetlights, and just like amusement parks, which were finding ways to entertain us at night. So too, the electric utilities figured out that they could sell electricity to businesses at night. And the big piece of that was important is that if you ran your capital equipment 24/7, 365, you could depreciate it much, much faster. You could utilize that equipment much more quickly to generate much more economic output. And as a firm, that's a really good thing if what you're doing is investing in capital equipment. And so what this did is it shifted the balance in the early 20th century between capital and labor in the economy, away from labor and towards capital. We have much, much more equipment, in large part, I might argue, because we had cheap electricity at night with which to run it. It reduced your costs as a business to produce stuff if you produced that stuff faster because you were running 24/7, and if you produced a bunch of it at night when electricity was really cheap. So what happens as we come forward? In the future, you know when the sun shines. the sun shines between 10 a.m. and 2 p.m. And so in that future, right, if we have an enormous excess of electrons, an enormous excess of solar electricity, because we're running half the world's energy supply on solar energy, between 10 and 2 every day locally. What that means is electricity during that time period is going to be really cheap. In fact, already right now in the springtime and in the fall, the state of California pays people to take electricity from their grid because there's so much solar already on the grid, and they're only at like 30%. They're not at 50% yet. But they give away electricity for free, and sometimes they pay people to take it in the middle of the day. And at night, it's going to be really expensive because how do you get electricity at night in this world powered by solar energy? Well, you have to store it in a battery or some other kind of storage technology. And that means it's extra cost. So electricity is going to go from a world that we've lived in for 100 years now, in which electricity was expensive in the day and cheap at night, to a world where electricity is cheap during the day and expensive at night. How is that going to affect our culture? How is that going to affect our economy? We don't know. But I think these are really interesting questions that we really need to be grappling with as we think about how do we design low carbon, not just energy systems, because that's not what we're talking about. We're talking about low carbon economies and low carbon societies. So with that, let me say thank you. I will stop sharing my screen here and we can have a conversation.